Welcome to impulse functions and their Laplace transform. So the general idea here is, so far, we have only considered forcing functions where the force is acting over a period of time. So essentially, there's a period of time, not just in a split moment, where the force is non-zero for the functions we've considered so far. So where the force is acting over a period of time. Now we want to see what happens if we have a force that acts just at a single moment in time. So what if we have a situation where a force essentially acts at a single moment in time? So an example of this would be force due to impact. Then we need a function that essentially denotes a force such as this. So we need a function to represent such a force. So we will bring into play impulse functions. So an impulse function delta of t minus t naught is designed to represent a force which is zero everywhere but t naught. But to have this force actually show up anywhere, the delta function, this impulse function, still needs to have a non-zero interval. So the way that we usually, or one way we can think about the delta function is as a limit. So essentially, delta of t minus t naught can be defined by a piecewise function fh of t, where fh of t is equal to 0 for t less than t naught. That's equal to 1 over h for t naught less than or equal to t less than t naught plus h, and is equal to 0 for t greater than or equal to t naught plus h. I apologize. I should have said that delta function was the limit as h goes to 0 from the positive side of these f sub h's of t. Then essentially what we're looking at is if we take definite integral from negative infinity to infinity of f sub h of t dt, this is equal to the definite integral from t naught to t naught plus h of 1 over h dt. And that really is just representing a rectangular region that we're taking the area of. It's constant function 1 over h from t naught to t naught plus h. This is equal to 1. So since we are viewing delta of t minus t naught as the limit of these f sub h's as h goes to 0. So since delta of t minus t naught is the limit as h goes to 0 from the positive side of f sub h of t, we say that the definite integral from t naught to t naught of delta of t minus t naught dt, we say that this definite integral is equal to 1. So this is not really a function we're used to working with in mathematics, in the sense that we are used to a definite integral from t naught to t naught of any function should be equal to 0. The delta function is designed specifically to have this definite integral equal 1. That's part of its definition. So let's go ahead and find the Laplace transform of an impulse function. So we will say that the Laplace transform of delta of t minus t naught is equal to the limit as h goes to 0 from the positive side of the Laplace transform of our f sub h of t. Those f sub h of t can be written using step functions, since it is just a piecewise continuous function. So f sub h of t, we don't start until t naught. So our first step function should be u of t minus t naught. And then it's multiplied by 1 over h. And then we're adding to that. The next place we change is at t naught plus h. So we should have u of t minus, then in parentheses, t naught minus plus h. And then we should multiply that by, we want to subtract off the 1 over h we already had, and then our target is 0. So we're multiplying by negative 1 over h plus 0. And this simplifies to 1 over h times u of t minus t naught minus u of t minus t naught plus h. I just factored that 1 over h out front. So now that we have that f sub h written in terms of step functions, we can simply look at the Laplace transform. So the Laplace transform of delta of t minus t naught is equal to the limit as h goes to 0 from the positive side of 1 over h times the Laplace transform of u of t minus t naught minus the Laplace transform of u of t minus t naught plus h. We know the Laplace transform of our basic step function. It is simply, if we had u of t minus tau, we had e to the negative tau s over s. So this is the limit as h goes to 0 from the positive side of 1 over h times, we would have e to the negative t naught s divided by s minus e to the negative in parentheses t naught plus h times s all over s. We can go ahead and pull out an e to the negative t naught s over s. So this is e to the negative t naught s over s times the limit as h goes to 0 from the positive side of 1 over h times 1 minus e to the negative hs, or e to the negative t naught s over s times the limit as h goes to 0 from the positive side of 1 minus e to the negative hs over h. So notice as h goes to 0, this limit goes to 0 over 0. And so we can go ahead and apply L'Hopital's rule. We get e to the negative t naught s over s times the limit as h goes to 0 from the positive side, taking the derivative of 1 minus e to the negative hs with respect to h. So taking the derivative of the top with respect to h and then dividing by the derivative of the bottom with respect to h. We wind up looking at e to the negative t naught s over s times the limit as h goes to 0 from the positive side of that numerator just becomes s e to the negative hs. Denominator is 1. This limit we can take. So we are looking at e to the negative t naught s over s times s. And we wind up getting that the Laplace transform of delta of t minus t naught is simply equal to e to the negative t naught times s. So we have this impulse that happens right at a specific point in time, and then it's back to 0. That Laplace transform is e to the negative t naught s. So in the next video, we will look at solving IVPs involving the delta function or impulse function on the right-hand side.